So in this problem, we have vehicle A traveling at 88 feet per second, vehicle B traveling at 81 feet per second, and the acceleration of A is negative 0.02 x feet per second squared, and the acceleration of B is 0. That means the velocity of B remains constant at 81 feet per second, and the velocity of A is deaccelerating as a function of distance. Vehicle A is 250 feet away from the intersection, and the intersection breaks off at an angle of 30 degrees. The question asks, what is the velocity of A at 250 feet and the velocity of B with respect to A at this time? Now, we have to analyze the acceleration equations and see what this problem is exactly asking. So if we take a look, we know that A can equal dv dt, or it can equal v dv dt, or dx rather, excuse me, v dv dx, or d squared x dt squared. Now it's important that we notice this is v dv dx. Let me rewrite that. v dv dx. Of these three acceleration equations, only one of them is going to allow us to separate variables and integrate with respect to position. Here, the deacceleration is a function of position. V dv dx will be able to give us the answer that we need. So if we take a look and see that it's negative 0.02x equals v dv dx, what we do now is multiply both sides by dx, and that gives us negative 0.02x dx equals v dv. Now, in this problem, the moment the timer starts, the moment all the measurements begin, essentially we're taking as if VA, even though it's moving, its initial position is 0 while it's moving, and its final position is 250 feet. And the velocity starts at 88 feet per second and ends at a V final that we don't know. So it's negative 0.02, the integral of x dx from 0 to 250 equals v dv from 88 feet per second to v final. See? So now, if we integrate that, that is negative 0.02 divided by 2 x squared evaluated from 250 to 0 equals v squared over 2 evaluated from VF to 88. These are all divided. There. Let me switch papers real quick.